Hey everyone, how are you all doing? So in this stream, we are going to continue building the projects from Nand2Tetris course. So the last stream where we did a project from Nand2Tetris, we built the program counter, which was from week 3. So today we are beginning with week number 4 and the projects inside that week. So it contains assembly language, and not just any assembly language, but the heck assembly language, or you can also say the machine language. So the first program that we are going to build is a multiplication program. So by default, this machine language doesn't contain the operations for multiplication. It contains addition and subtraction, but we don't have the multiplication functionality. So that's what we are going to build in this stream. We will be using the functionality that is available inside the language to simulate the multiplication, or can say achieve the functionality of multiplication. So let me first open up the assembly language file. It should be inside, let's say, week 4 section. Field mult. So this mult.sm is the assembly language file that we have to modify. So let's open it up. Mult.asm. By the way, before we get started, you also have to open up the CPU emulator, which is basically what we will be using to run this assembly files. So let's, and this is a different software from the one which we used in the previous stream. So that was the hardware simulator, but this one is the CPU emulator. So let me open it up. So this is the software that we will be using to run the assembly files. Okay, now let's open up the file. Let's keep this aside for now. So I think first we should try writing the pseudocode. So let me write the pseudocode inside this file only. We need to write a multiplication program. Okay. Let me open up the slides. So these are the kind of commands that we can use to program our computer, hack computer. So as you can see, the computation part only contains and or operation and addition and subtraction. It doesn't contain division and multiplication. So we will have to create our own implementation of multiplication. This is the kind of program that we are going to write. So we have three registers D, A and M that which we can use inside this assembly language. D is just for the data and A can carry an address as well as data, and M will have the value of RAM A, and A is basically this register. So whatever address, if we place address inside this A, then M will have the value of the RAM at which this A address points to, right? And this value points to basically a 16-bit register. This is a simple program which adds two numbers. So first it selects at 0. That means when we write at 0, at and whatever value, then this operation will save the value which we specify over here into the A register. So after this first operation, A will have 0 inside it. So after that, when we fire D is equal to M, now M points to RAM 0 because RAM 0 because this 0 comes from this A register. Okay, so D will have the value of RAM 0, where 0 is the first register in the RAM. And after that, we select the first register, and this memory M points to that first register now, and now we can do D plus M. So D already contains the value of RAM 0, and now we are adding RAM 1 value to it and again saving it inside the D register. So now D will have RAM 0 plus RAM 1, and we can again save this D register to another memory unit, let's say 2, and we can select the 2th register using at A is equal to 2. Now this M points to the second register, so we can save the value of D inside M. So that is how we can add two numbers. So instead of using 0, 1 and 2 up to 15, we can use R0, R1 up to R15 to select the first 15 RAM registers. So as you can see, instead of at 5, we can use at R5, but we are not using at R7 over here because this is not an address that we are specifying. This is a value which we are specifying, and we want that value inside the data register. Therefore we don't point it to any RAM. Other built-in symbols are screen, keyboard. We don't need to worry about screen and keyboard right now. We will see it in the next program. So right now I'm just trying to review all the different commands that we have available, because I have not used them. I have just watched the week 4 section, so but I don't remember all the commands, therefore I'm reviewing it so that we can start implementing the multiplication program. Right, we can use branching inside this program as well. These are the kind of commands we can use for branching. JGT means jump if greater than 0. We'll see how it exactly works. So we can use this kind of labels. So I guess I will have to read out what it does. So this command basically first saves 8 inside A, and when we fire up this command D and jump greater than, so what it will do is basically this, it will evaluate first this D, and if it is greater than 0, then it will go to this address 8, which is this command. So it will execute from this thing. It will bypass this whole set of commands. But if this condition is false, then it will continue with this command, these commands. But this specifying the number of the command line gets confusing, so therefore the authors have provided this kind of functionality, declaring a label. So now we can just use this kind of label to jump to this command. We don't need to worry about what the command line number is, which is 8 in this case. So previously we used @8 inside this command, but now we can directly use @positive, and @positive is over here, which basically starts the execution from this command if this condition is satisfied. So that's the thing about branching and labels. After that, let's see what we have. By the way, in this assembly language, we have to specify this kind of AND condition as well. This is basically a loop, an infinite loop. When it comes over here, 0 jump. First it saves and this label inside the address register, and this jump is an unconditional jump, so it will jump to whatever a variable holds. So a variable holds this line, so it will continue looping over these 2 lines, and if we don't do that, then our program will try to access all the memory units. It will go on and on and on. So therefore we have to write this kind of AND condition. So we have the functionality of using variables. So let's see how we can use this kind of variables at and the name of the variable. So when we use variable, we don't have to worry about the address of the memory or the register which we are using. It will, the assembler basically does it behind the scenes automatically. So that's one less thing we have to worry about. So as you can see, this at temp gets translated to at 16 behind the scenes, but we don't have to worry about if we use the variables. And this variable starts assigning from 16th register, so 16th and so on. So the second, if we use a second variable, it will be assigned at 17 address. Okay, we can also use this kind of loops. This is a pseudo code, but let's see how we can use loops inside assembly language. So we can use these jump conditions to provide the functionality of, or you can say simulate the functionality of loops. So this is the condition that we are using. First we are is the different condition, let me check. It's over here. So at loop and unconditional jump. So first we specify the address, which is this one, and then we unconditionally jump to this label. So it will jump loop on and on and on until we until this condition is specified, till this condition is satisfied. So if this condition is satisfied, greater than JGT means greater than, jump if greater than. So if greater than, then jump to stop. So that will stop our loop. That's how we can create a loop. Let's see what more they provide. Program execution, writing, assembly, pointers. Yeah, we also have the functionality of pointers. From this portion, the screen section starts, so we don't need to worry about screen right now. Screen and input output and handling the keyboard, we'll see it again in the second program. So that's basically it for the machine language of hack programming computer, I mean the hack computer. So let's see how we can implement the multiplication now. First we will write a pseudo code for the program. Let's see what we need to do to get multiplication functionality. So to get multiplication functionality, suppose we want 2 3 times, then we can do we can achieve this functionality using the addition as well. So we can do 2 plus 2 plus 2 3 times. This will basically give the same answer as 2 times 3. So let's see, 2 times 3 gives us 6, and this gives us 6 as well. So this is how we can use the addition functionality, which we already have available inside the hack machine language, to simulate the functionality of multiplication. So let's write a pseudo code for it. So first we will have two numbers. So first we need to store these two numbers. We will store them inside a variables. So let's say we store it inside first n1 is equal to n1. Store the first value inside n1 and the second value inside n2. We will see later how we can translate this into the machine language. First we are trying to write the pseudocode. So after we have got two variables, we will need a loop to, and that loop will basically run for either 2 cycles or 3 cycles. So we can also, so this functionality we can also provide like this. We can also do 3 plus 3 twice, which will give us the same answer, which is 6. So we can either loop through this number of times, 3 number of times, or we can loop through 2 numbers of time, and that many number of times we will add the second number to itself, right? And at the end of the loop we will have this answer, which will basically be the multiplication of both of these numbers. So we will need a loop. Let me write loop like this, and the condition will be like if I, so we will also need an I variable. So let's write it inside the pseudocode. I will be 0 initially, and if I is greater than, let's say in this case well, we should start with I is equal to one of the numbers, right? Maybe we can do something like this: I is equal to less than equal to less than 0 1 2, okay, less than, let's say n1, then it should be greater than n1, then go to n. So when it is greater than n1 is 2. So suppose we are using this this kind of functionality. In that case we will be using n1 as a looping variable. So if first we start I with 0 1, and when it comes to 2, I is equal to 2, I think at that time this condition will be false. Should I say greater than or equal to over here? We'll see later. That's a small detail which we will have to worry about later. So let's see, go to end. Now that is for the last case, but if that case is not satisfied, then we want to do, let's see what we want to do. We want to should we get another variable? Alright, let's get another variable for sum. So we'll get a sum variable as well. We don't need another variable, but we'll just use it just for the heck of it, to not make our program more complex. We can optimize it later. So that's that sum, and what we want to do is sum, the previous condition is not satisfied, and we want to do sum is equal to sum plus this second number, which is n2, right? And after that we want to increment the I variable. I is equal to I plus 1, and after doing that we again go to loop. And finally we can end the loop and the program. Go to end. So don't really end the program, it just runs in an infinite loop until we terminate the CPU emulator. So that's one thing. So first we need to get these four variables I should say. So let's see how we can get those variables. First let's get the I variable. So to get the I variable, first we have to place 0 inside. So 0, first we select 0 inside M, and now we pass, let's indent it. So at 0 and D is equal to M. This will place 0 inside the data on D register. Now we create a variable I, and M is equal to D. This will basically place 0 inside the I variable. So now we have I is equal to 0. We need to do the same thing for the sum variable. So let's see. Sum. Now we have sum variable as well. Now we need two n1 and n2 variables. So let's see how we can get those. The values of those variables will be given by the users, so we don't need to manually provide the value, but we still need to write this something for those variables. Do we just have to get the pointers or something? Let me see. Alright, so this is the example which you can use. Let me try to write the loop right now. We'll worry about n1 and n2 later. So to write the loop, first we will get the loop variable, loop label like this. And now let's see what we need to do. We need to check this condition. We need to check I greater than n1. So for that we have to do I minus n1, which will give us something. So first we need to get I like this. So let me select I again, iterate I. This will select I. Now we need to get the value of I inside the data register. After we have got it inside the data register, now let's select the value of the first n1, which will be inside R0. Now what we will do is D is equal to B, which already contains the value of I, minus M, which contains the value of R0. So it will be basically I minus n1. I minus n1. Okay? We have the I minus n1 inside D. Now we need to specify the stop condition. Stop condition. So let's see what we can use. We have to check stop condition on this D register. So we provide D over here. Now what we want to do is jump is greater than equal to, right, JGT. So if I minus n1 is greater than equal to 0, which will be the case when I is greater than n1. So if I is 2 and n1 is also 2, then it will be 0. This will run the loop for, let's see, if I is equal to 0, the stop condition won't be satisfied. If I is equal to 1, the stop condition won't be satisfied. If I is equal to 2, then again the stop condition, it won't be satisfied because it is not greater than. We can use greater than or equal to. Yeah, we can use greater than JGT. Instead of using JGT, we can use, I think, J greater than or equal to. Do we have that kind of jump condition? Let me check. Jumping condition. Yeah, so these are the jump condition. J equal to, it is J equal to is jump equal to, want to check the table which specifies what this exactly means. Okay, this is the table I'm talking about. Jump, yeah, it's greater than or equal to JGE, greater than or equal to. So we can use JGE over here. So now the loop will run for 0 when I is equal to 0, when I is equal to 1. So it will run 2 times only if n1 is equal to 2, and that's what we need. So let's continue now. That's the example which we were referring. Yeah, it was this one, right? So now if this condition is satisfied, it will jump to stop. Now we have to write the label for jump as well, stop as well, I mean. So let me write it over here. STOP, stop. So let's see what we want to do when the loop stops. We want to save the value. So let's worry about stop later. Let's complete the loop. Okay. It will be better if I write some comments over here as well. If I is greater than or equal to, and then go to stop, right? So if that is not the case, we want to sum, we want to do this kind of sum. So to do that, first we have to get this sum variable. We already have it. It is initialized to 0. So when we get the sum variable, we have to first get the sum variable, and inside that sum variable we have to append n1, n2, value of n2. So let's first get the value of n2, which will be inside R1, right? Now let's place it inside the D register so that we have it available when we get another variable, which is sum. Now that we have sum variable, what we want to do is this sum variable m should, can we do m is equal to m? Yeah, we can do that. M is equal to m plus d. This will basically add this d, r1, the value of r1 inside sum. This will be 0 plus whatever the value is inside r1 initially. We will have the value inside m later. Now after that, what we want to do, we need to increment the I. So after that we have to get I, and after getting I, we can do m is equal to m plus 1. This will increment the I. and again we jump to loop. So to jump to loop, again we have to specify at loop, and we jump unconditionally to loop. And now we can go and create the stop condition, or I should say the stop label commands. So let's see what we need to write inside stop. We need to get the value of sum, and we will place it inside the data register. And now we again select R2. This is where we will place the final result of our sum. So M is equal to D. That's the end condition. Yeah, we didn't create it yet, I guess. So now we only need to implement the end condition. So this is how we can do it. And 0 jump unconditionally. Alright, so it seems that we have a working example of a multiplication program. Let's see if this works or not. We should try to load it inside the CPU emulator. Nand2Tetris. So let's now place 2 inside 0 and 3 inside. So remember this 0 is R0 and 1 is R1. So we have placed 2 and 3 inside this values. Now we expect 6 inside this second tooth register. So let's see if we get it or not. Oops, it seems that we didn't get the expected value. So let me do no animation and check why we didn't get it. But not resetting the values clear. Yes, I want to clear. Let's try to run it without any animation. Wait, it's not even running the program. Okay, because we have not given any value. So we need to give values inside this. Why is it not accepting any values? Let me try to load it again. Is there a bug or something? Because it seems that I can't even edit the values of this registers. I can't even reset it. Let me close it and open it again. Load the program again, multiplication assembly. Okay, now we can edit the values. So let's step through the program one by one. So first we do at 0. So this will select 0 inside A, and we do D is equal to M. So the 0 will be inside this. Wait, this should have been at 16. Let's see, at 16. That places 16 inside A. By the way, why did we do at 0? Check at I. Where is at I? We have specified at I over here, but I can't see at I in this case. It's over here. Why is our code jumbled like this? Alright, wait. Yes, this at 16 is at I. So now this 16th will be 0. Wait, but it is not 0. It is changed to 2. Why? Alright, I see what is happening. We're selecting this. Yeah, I get it. This should be A, not M. Let me try to load it again. Now let me run it directly. Why did we get 6? Why? It should be 6. I'll let it run. We'll see. We got 8 inside this second register. Now we should be getting 2 3s are 6, but we are getting 8. So where's the bug? So this time we are going to step through it one by one. So first we load 0 inside the 16th register. Right. Now we select this 0th. Right, here also I have to change M to A. Right. So I will have to load the program again. Let me clear the RAM and provide 2 3 again. Now let it load, let it run by itself. So now we are getting 6, which is the correct value. So let's try different values. So let's type 10 paisa. So we should be getting 50 inside this register. So now let it run. Awesome, we are getting 50. So the authors have also provided the test script. So let's load the test script, this one. Let me first clear the values and reset the program. Now we can load the test script. This test script basically provides very different inputs. It will check if our program is working properly or not. So let it run then. Six 7 the 42. Awesome, the comparison ended successfully. So we are getting this message. That means our program is totally bug free. We are getting correct. So this is the output we are getting for 000 or 100, 2 40 20, 3 1 3, 2 4 8, 6 7 42. So that means, guys, we have a complete working multiplication program. At this point we can start building the second program as well. It's been only 1 hour, so I guess we can start building it. And if we can't build it in less time, we will continue building it in the next stream. And in this program we have to build, let's see, illustrate low. So now we will have to use the screen and the keyboard devices as well. So we will see how to do that. The program runs an infinite loop that listens to the keyboard input, and when a key is pressed, any key, the program blackens the screen. That is, writes black in every pixel. So when a key is pressed, like this, E, F, or whatever key is pressed, this screen will turn totally black when we press a key. When no key has been pressed, then it turns to white again. So that's the program we have to write. The screen should remain black as long as the key is pressed. Okay. And when no key is pressed, the program clears the screen. Implementation note: your program may blacken and clear the screen in any spatial visual order as long as pressing the key continuously for long enough results in a fully blackened screen, and not pressing any key for long. Okay. So first we'll try to blacken the whole screen, and if that is successful, we will try to implement different kind of patterns in this screen. So let's open up the screen program. Let me close this one. Should go inside the fill directory, fill automatic. Let's open up fill ASN. So as always, we'll start with writing the pseudocode. But before that, let's review screen and keyboard inputs, because we stopped at this point previously. So if this is the RAM of our hack computer, then this portion of the RAM from 6384th register and up to for 8k total registers. Is it 8k? Wait, is it 8k? So whatever the values inside these registers will be. So if it is 0, the screen will have white screen, and if it contains 1, whichever register bit contains 1, then it will map that point in the screen as black. And if we can check how they are exactly mapped, it will be helpful. So let's see, to see how those bits are exactly mapped to the screen. So we can check should be in the previous slides, so let's check it. Variables, branching, it's over here. Memory mapped output starts from, let's see, program, machine language, input output, memory mapped output. So it starts from this base address 16,384 in our hack computer, and this first register, which is specified by this address, base address, this is of 16 bits. So this 16 bits will map to this first 16 bits. So this screen is of 256 by 512, 256 column and 512 rows. So this will be mapped to this first 16 pixels, this 16 bits to next 16 pixels, and so on and on up to the last pixel. So it will be stacked like this from left to right and top to bottom. And these are basically the computations that we can use to select the specific bit. So this word, this computation, let's see what it does. To set pixel, row and column on and off. So if it is the first row, let's see what this actually does. RAM, we are selecting the RAM, this RAM. We are passing in this base address 16,000, and after that we are adding okay, I get it. So we are checking suppose we want to check where does this pixel, which is specified by a 0th row and 0th column, lies inside the memory. Then we can use this equation. So if we place 0, row is 0 and column is 0, so we should place this 0 inside here and here, so this whole thing will compute to 0. So it shows us that this bit is inside this RAM 16384, which is intuitive, because you know it is the first pixel, so it is definitely inside the first register. So let's check a different column. So let's say if we select first row and fourth column, so if we place it inside here, row is equal to 1, so 32 into 1 is 32, and column is 4, so 4 divided by 16. So let's see what it gives us back. 4 divided by 16.205. So let's see how it maps. Okay, so this will we are getting the, what is it called, the remainder part or the exponent quotient, or what it is called, 16 into, I don't know what is called, but this will 4 by 16, this computation will compute to 0 for this part. So it will be this plus 32, because this part was 32 into 1 is equal to 32. So this plus 32 will be this second row, I guess. Now why is it second row? Sorry, not second row, this row, 16384 plus 32. Now why that should be the case? So if we see, there are 512 columns in pixels in total in one row. So, and we have 16 bits inside one register. So 16 into let's say we have 512 divided by 16, so that should be 32. So that's the reason we have 32 into row, and this is for the column, whatever will be the, I don't know what it is called, let me check the terms. Quotient, remainder, division, to check what it is called, dividend, divisor, and it should be either the divisor or dividend. Dividend is this, divisor is this, and 6 is quotient, and remainder this. So yeah, we need to get the quotient part in this computation. So the quotient part of 4 by 16 will be 0. And this is how we can select a particular bit inside the register that we selected. So suppose in this case we selected the 32th RAM register, but we still need to check where does this particular pixel, which is specified by first row and fourth column, lies. So for that we can use column %16. So this will give the remainder of this column %16 will be the remainder of 4 by 16. Column was 4, so 4 by 16 will be, let's see what will be the remainder. It will be 16, right? Or wait, what will be the remainder of 4 by 16? Check Python for modulo 16. It gives back 4. Okay, so the modulo of, what is it, 4? Modulo character. Check modulo. What does it do? Modulo character. Of course, yeah, I get it. Why we get. So this 14, if we select this pixel, particular pixel, which we set is specified by the fourth column, then this will be 4 over here. So 4 modulo 16 will give us 4. So that means inside this register, RAM 32th register, which is, I mean, the 32th register is specified by RAM 32, RAM brackets 32, and inside that this fourth bit is mapped to this particular pixel. So yeah, that is how this memory is mapped to this screen, right? RAM I is equal to what? Yeah, that's what we did. What is I over here? What is I in this case? Okay, it doesn't matter. That's for uh, uh, saving different values, so don't need to worry about it right now. Let me close this. So now let's see. So we have checked how the memory from RAM is mapped to the screen. So and one more thing I want to mention, when we change, so after we have got the particular bits, now we can change this value from 0 to 1 to 1 to 0, and accordingly the pixels on this screen will be changed either from black to white or white to black. If it is 1, the pixel is 1, then the screen will show 1 inside that particular, it will show black inside that particular pixel, or else it will show white. So that's it for the screen. Now let's check the keyboard. So for keyboard, it is like when no key is pressed. So when we press a particular key, a scan code of that key, a specific scan code is sent. So just like the screen has been mapped to a particular area in the RAM, which started at this address 16384. This keyboard also starts, this keyboard also has particular area inside the RAM. But for keyboard we don't need many register. We just have a single register of 16-bit. And let me check where it is. I want to check the particular address where the keyboard is mapped. Maybe it is specified later. Alright, we will check it out later. So I know basically that it is after the screen. That's what I'm sure of. So when we press a particular particular key on the keyboard, the scan code of that key will be passed to this array. So if it is 75, it will be converted. So this will be represented in a binary inside this register. So this particular binary bits converts down to 75 into decimal. So that's that. And when no key has been pressed, then the resulting code is 0. So we have all the zeros inside the keyboard memory area. And these are the scan codes, particular scan codes for different keys. Each key has a specific scan code which we can use to classify different keys. We can check the value inside this memory register, and if it converts to any of the scan code, then we know which key has been pressed. So yeah, this is the address. This is the address of the area where keyboard register resides. 24576. You can scan the values of this RAM register to get the scan code. So I guess that's it for keyboard as well. We should start implementing it now. So let me go back to the project again. Was it? Yeah, it's this one. So when a key is pressed, so if I press F on any key, so in this particular program that we have to build, we don't need to worry about any specific key, because we only want to check if any of the any key, doesn't matter which key, if any of the key is pressed, we want to change all the pixels of the screen to black. So basically we want to turn on all the pixels, and if that key, and we want to keep these pixels black while the while the key is pressed, the screen should remain black, and when we release the key, the screen should turn white again. So let's see how we can do that. So let me write something like a pseudocode. We need to say get a variable or something, the key, and it will get the value from the screen. No, it will get the value from keyboard, which is kpd. So we have the particular scan code inside this key, and we need to go into a loop. So Oops, that's not what I want. I want to check the, where am I? Nand2Tetris projects for cell multi. So here also we will need a loop. So let's get a loop, and inside this loop what we need to do, first let's write a stop condition, and it will be something like this: if we don't need to stop it, so we can keep running this loop infinitely, and in this case we won't specify an AND condition. So yeah, we don't need to specify the AND condition of this loop. But what we want to do is check the value of key. If key not equal to 0, that if it is not equal to 0, what that means is all of the it means that a particular any key has been pressed. So in this case we want to go to a particular function, let's call it fill, right? So now we have to write the pseudocode for fill as well. This will be a function as well. Well, in this case I shouldn't say function, but just let's say a label. So here what we want to do, first we want to, so this will select first all of this, it will select the screen and fill it with ones. So when I say select the screen, I mean it will select the RAM area where the screen has been mapped. So let's check out how we can select the screen. This is how we can select the screen. First we can get the address. So this variable is available inside the head machine language, which will map to that particular RAM register, the base register. This will give us the base register. So we'll also do the same thing, get it inside address register, the screen address. After that we'll again have another loop, so we will call it fill loop or something. Let's see. What we want to do is we can have this same loop. does this do? If I is greater than n, and what will n get, n will have? So in this case we don't need this kind of loop. We want to turn all the pixels of the screen on. So we want to loop until we hit the last register, and when we hit the last register we need to end that particular loop. So how do we check when we hit the last register? We can keep track of it inside this I. So let's get this kind of variable first. I is equal to 0. Right, now go back. This code is on slide number 99, so I will get back to it again. What I want to check is how many in total rows we have. This is for the keyboard. So in total we have 8191 rows. 0. We will increment this register this many times until it hits this last row, 8191. So 8191, right? So it's on the 53rd slide. So let me tell you what I want to do. Basically I want to loop through this function, or this loop. I want to loop it 8191 times, and each time I want to increment this address by 1. So next time it will point to row number 2, and next time row number 3, and so on up to this row. And when we select a particular row, we want to turn all of the values to 1, and we want to do it for every loop. So it will turn all of the pixels of all of the bits of all of the rows 1. So I hope you guys can get it. Get back to 99th slide. 97, 98, 99. So let's see what we will do. Yeah, let's write the loop. Let's call it I guess F loop, for fill loop. What this fill loop will do, it will check So let's get a variable where we can place the number of rows. We can hard code it as well, but just for the sake of it, we will provide the same kind of functionality. So we'll place it inside the first register, and here we will place 8191 for all the rows, right? And now we want to check for this stop condition if I is greater than n, then go to n. So let's see what this will do. If I is greater than n means if I reaches 8191 0 greater than or equal to, yeah, greater than is all right. If I is greater than n, and then we want to end this loop, or else let's say what we want to do in the else condition. If it is not greater than, then we want to get the way RAM by this address ADDR. It will give us that particular RAM, and we want to -1, want to fill that RAM. After that, in the example, they are adding 32 because basically they are going to the next row, but we don't want to go to the next row. In our case, we want to move to the next row of the RAM, not the next row of the script. For that, we only have to increment it by 1. Right. Now let's see what we have to do. Yeah, we have to increment the I. So I will be I plus 1. And we will again go to F loop. And at the end, we will have yeah, in this case, so we won't be having an AND condition or something. What we want to do is, if the key is pressed, if not equal to 0, then we want to run this fill function, right? It will fill all the so after this, we don't want to end it, we want to go to the loop again. So it will be loop in this case. Go to loop. We won't have an AND condition. We go back to this, right? And now again, if the key is not equal to 0, we'll keep it filled. And we also want to check a condition where the key again turns to 0. In that case, we will have to unfill the screen. So for that, let's write different condition. If key equal to 0, then go to on field, which will be the same as field, but we only have to pass -1 instead of we'll have to pass 0 instead of -1. So I'm thinking that we can use the same function to field and unfield. So, and we won't provide this -1 directly. We will maybe keep this value inside a particular variable, and we will change the value of that variable to -1 or 0 based on these conditions, right? So yeah, let's do that. But how can we do that? Suppose we initialize this variable val is equal to -1. Maybe it should be 0 by default, right? Now if key not equal to 0, we should move this thing here. Key is equal to 0, key is equal to 0, okay. Let's see what if we do this field this for filling, and this is for this is the filling loop. Say suppose I write a different label, let's say b black, and here I change the value of val is equal to -1, and I have another, and after that I go to field, which will be an unconditional jump, and I have another way label white. This will set value to 0, and this will again have unconditional jump to field. And in this case we don't need to go to field because it is after this statement only. So we'll see, we'll check later. And in that case we will have to change this. So when the key is equal to 0, that, let's see what it means. When the key is equal to 0, then in that case we have to go to white, right? And when the key is white, when key not equal to 0, then we have to jump to black. So this implementation seems correct to me. And over here we won't be providing -1, we will have val to this RAM address. Ooh. The pseudocode seems logical, and it seems that it might work. So let's try to write the code for the pseudocode now. Let me get rid of the bottom pane. Okay, so first we need to get this key KBD. So we have this memory register of keyboard available inside this KBD. I just need to recheck it as it is inside KBD or something else. Yeah, it is inside KBD. Are they providing any example for that? Alright, let's just get it. So first we'll need to get KBD. This will have the memory register of keyboard. And let's place it inside the data register, the value of KBD inside data register. Now we need to get a key variable, so let's get that at key, and well, should I get a key variable right now? Well, it's alright, I can get it. So I will place it inside, place the k value of KBD, which is inside the data register, inside the key register, which is selected by the M register. Now I have the value of KBD inside key. Now let's see what we want to do. We should be getting these values inside every loop. So I guess we first have to write the loop. So let's first get the loop. This will be an infinite loop. Now that we have got the key, we can check the condition if key is 0 or not 0. So let's see how we can check that. We have the key register selected, right? So can do m, and if m is equal to 0, need to check if it equal to 0. So j eq, I think that's the command. Let's check jq. Yeah, we are on the 100th slide. We'll get back to it again. I want to check the jump command. So what is j eq if equal to 0? So yeah, if we jump equal to 0, where do we want to jump? So that's what we have to specify over here, where we want to jump, and we want to jump to white. In this case we have to provide a capital label. It's not required, but it will be easier if we keep the labels as capital and the variables as smaller case, I mean. So if equal to 0, then we need to move to white, and if not, if that's not the case, what we need to do, we need to get the black variable, black label, I can check the same condition again. Jump is not equal to 0. Or I can just unconditionally jump. Yeah, that will be good. So in this case, if it is not equal to 0, then it will continue with this command. It will store the address value of black and unconditionally jump there. So now we need to write the black and the white commands. First we'll write black. Now what we need to do inside black, first we need to get a value this val variable, and we need to place 0 inside it. So let's say first get 0 and we place it inside the data register, and we get the val variable, and inside that we place t, which contains 0. So now we have initialized value. After that we get kbd a, change the data register, get the key, place it inside key. Awesome. Now inside black we have to change the value of this val register. We'll change it to -1. So let's see how we can do that. First we need to select the val, right? So we select the val. Now after that it is inside a. So m is equal to -1. Can we do that directly? M is equal to -1. I think we can do it. Yeah, I think we can do that. Or not. Let me see. Can I specify M is equal to -1? Yeah, I can select the destination as M and the computation as -1. So yeah, we can do this thing. M is equal to -1. This will place -1 inside this val variable. So now we have -1 inside val. Now we want to unconditionally jump to fill. So we can select fill M0 JMP. That's it for the black. We also need a white, so let me copy the same thing. Inside it we need white. For white we will select M is equal to 0. Hello Albeman returns. Well, yeah, I did go to college and I did select CS, but I didn't complete it. I dropped out. And this is me basically trying to learn how this computer works. So I'm doing this course, build a modern computer from first principles. And this is the project of fourth week, and I'm building this field assembly language. And before that I created this different projects. The first week consisted of creating this kind of chips, Nand, not, and, or. So are you a CS major? Alright, so in case of white we need M is equal to 0. And we will again unconditionally jump to fill. Now we have to create this fill label. Fill. Let's see what we need to do inside fill. First we need to get the memory register of screen inside the address. So let's do that. The code for the same was on 99th slide, I guess. So over here you can get this variable screen. Add screen. Now screen d is equal to a. This will place the value of screen inside the data register. Now we need to get it inside the address register, ADDR register. So let's get this variable ADDR, and inside that pass the value which was inside the data register. Now we have the value of screen memory register inside ADDR variable. Let's see what we need to do now. We need to get I variable. This is for the looping part. After that we will also need to get this register 0 inside N. So let's first get the I variable. At I Wait, before we get the I variable, we need to get 0 value inside the data register. So let's get that first. 0. Now data is equal to A. Now that we have 0 inside D, we can do M is equal to D. This will place 0 inside I. Now we have 0 inside I. What we can do, we need to get N variable, and inside that we need to place the value of RAM 0. First we need to select the value of RAM 0. So let's get that at R0. This will provide us R0. We'll place it inside data variable again. Now we will get N variable, and inside that we'll place the value of R0. Awesome. Now let's see what we need to do. We have got the value of inside N as well, which will be the base, or I should say the last address, the last row of the screen memory. Now I need to implement this loop, F loop. Inside this loop we need a condition where we check if I is greater than N, then we need to end this loop and go to the first loop loop label. And if that's not the case, then we need to change the value of RAM address to well and increment the address and increment the I. So let's implement this thing now. We need a loop, right? Throws a loop, and we need to check the condition if I is greater than N. So how can we do that? First we need to get the value of I. So this is how we select the value of I. We can place it inside the data register. Now we select the value of N, and we do, let's see what we can do. B is equal to D minus M. This will do I minus N, and Now we need to load the value, load the address of loop, and we want to jump to this loop if d is, let me check the condition again. If I is greater than n, go to loop. I is greater than n. I is greater than n. So that means so we can use j g t over here. So if it is greater than n, we will jump back to this loop over here. Now if that's not the case, then we load the value from this val variable, inside this RAM address. So first we need to select the val variable. So let's select that val variable and we'll place the value inside the data register. Now we need to select the let's see, the RAM register which the address value points to. This address value points to. So we need to get this address value now. So we'll get ADDR will give us the address value inside address. And I can directly say m is equal to this value. Value is inside d, so m is equal to d. This will change the RAM register at that particular value. I hope so. I also hope so it does that. This will select that particular RAM. Let me see if it works like that or not. I need to check. Yeah. A is equal to m. M is equal to -1. Why did they do that? We are first placing the value of m inside A. Oh. Alright, I get it. This is a pointer to that RAM. So we don't want to change this address value. We need to change the RAM where this address value points. So for that, after we select this ADDR, we need to place it inside the value of it inside A. Now this M points to that particular RAM. Now we can do M is equal to D. Awesome. It would have been harder to track this bug if we didn't read this part of the code. Now we need to increment the address value and I value. So again we have to select address, now what we can do, we can m is equal to m is equal to m plus 1, right? I can do that. M is equal to m plus 1. Now after this thing, this will increment the address value. Now we need to increment the I value. So let's get I. We can do m is equal to m plus 1. This will increment the value of I. After that we need to what we need to do, we need to jump to f loop again, right? So this will be an unconditional jump. Let me check if I want to jump on it. Also this should be semicolon. And go to f loop again. Right, it seems I have written the whole code as per the source, as per the pseudocode I wrote earlier. So let me try to run this program. I'm sure there will be many bugs and it won't work as expected. Since this field as a line 55 expression expected. Is it expecting an expression? Line 55. Okay, so I made the same mistake over here as well. It should be semicolon. Let's try to load it again. On line 61, expression expected. Damn, how many times did I commit the same mistake? Good. Now let's see. I need to clear this. I need to, let's say, let's give just 5 value inside this row and let it run. Oops, what happened? It stopped. Why did it stop over here? Stopped at this step, which is what? Why did it stop? I think over here when we wrote It should jump to field, but it is not jumping. Why? We are 20, right? But it is 19. Why is it showing 19 over here? It should jump to 20. Why did it stop executing? Well, I see there's a flickering of happening. That means it is looping. Our program is running, but just stays at this position. What's the problem? Let's see if I press 9. Well, at least it should go back to this loop. I think I have a logical bug. Let's step through the program one by one. At 0, here we are initializing this val variable. Now we are getting the keyboard. And we are placing the address inside the 17th KBD, inside the key. Right? Now what are we doing? We are selecting white. Wait, why do we have 16 twice? Shouldn't this be... Wait, okay, yeah. It's a label, not a variable. We are getting 16 in the address variable. After that, we are jumping if wait, I have selected m over here, and m is this value key if jump is not equal to. So if it is not equal to 0, this value 17 is not equal to 0, all right, I see what's the case. I am changing the value of this a to 16, but this condition is now checking this value with equal to 0, but we need to check this key value equal to 0, which is this 16th value. So that's the problem. I think that's the issue, right? So let's see what this does at white. This will select at 16 at this number 2a, and at this number is this 16. So we have 16. Now we are checking it. So I need to check with this value. So let me change this thing. I'm doing m is equal to d. At key, first I'm selecting the key and I am placing the value of KBD, which was inside data register, inside that m. Now I'm selecting at white. So I should change this m to t. Now let me try to load it again and see what happens. Let's clear the inputs. Let's again give 10. No animation, fast. Oops, great, we are getting a line, but we are getting this line even though we are not pressing any key. So that's an issue. Let's see how we can fix that. And this time let me not give 10. Let's give, let me first clear the inputs and reset the program. This time we will, do I have to load the program again? Damn, I can't even. Oh, I hate this CPU emulator. I have to restart it again. Let me provide 8191. That was the value, right? Let me check. What was the last value of the value of the last row of the screen mapping? Eight one nine one. Great. Now let me try to run the program. It is running. What if I press F? It is showing just a small line. That means my program is not running, and definitely it is not looping over anything. Now, why is that happening? So after I filled it for one time, I went through this loop. Wait, am I not jumping again to F loop? Does this thing? Yeah, I should go to F flop again. Am I not doing that? Yeah, I did that. Wait, add them. Okay. I'm jumping, but I'm not providing the value. So that's the issue. I have to load flop. There are very minor bugs, but those are very hard to track. And again, I will have to load it again. Cannot to reset it over here. What the hell is this, man? Can't even provide the value. I have to restart it again. Oh, the CPU emulator sucks. Load it again. Give 8191 value. No animation. Fast. Let it run now. Oops, it is changing the screen even though I have not provided any input. What if I change the value? No, nothing seems to be happening. So let's see what is happening. We'll have to step by we'll have to walk through the program step by step. So we'll have to clear this again. Damn, man. Why can't I provide the value? Okay, I have to change it to program flow. Oh, I'm grateful I found this thing, or else we will have wasted a lot of time just restarting the program. This time let's give it 8191 and let's step through program one by one. First we select 0, place it inside data variable, select 16 for value variable, and place 0 inside it. Right, now we select the keyboard, get it inside data, select the address variable, and inside that variable place the value of keyboard. Now we are getting key, any variable key. Okay, right, we already did key value. Now we are just selecting the at white and placing it inside A. Now we are checking D, and D is 245. Okay, I get it. We don't have to check the address. We are checking the address for this condition. We have to check the value of this value where this address points to. So that's another thing. So let's see, after this what do we have to do? I have the value of key inside M, right? That key, that means the value of this variable key inside A. Now we are changing that value to D. So now that Okay, we don't need to change the value of t. Wait, I'm confused. Let me walk through it step by step. First, we are getting the at key kbd. Now this at kbd will load 24576 inside a, and we are passing that value to data. Now we don't want to pass this value to data. We want to pass the memory, the value where this address points. So this should be d is equal to m. So let's change it. D is equal to m. Now we can do add key. Now we can select add key and pass m is equal to d. So let me save the program and load it again. I need to clear the input. Let's pass 8191. Let it run by itself this once. Cool. So this time it is not filling up the screen. Now let's try to press a key. Awesome. Now if I release the key, the screen goes to white again. Now if I press again, it turns to black. If I release the key, then see my hand. Now I'm pressing the key. You can check this area as well. This will show us which key has been pressed or if any key has been pressed. So right now it is blank. That means no key has been pressed. Now if I press any key, F has been pressed. So I'm pressing F key right now. My finger is on the F key and it is pressed in pressed condition. So for pressed condition, screen remains black. Now if I release the key, watch this section and the screen as well. If I release the key, cool, it turns to white. Press black, white, black, white, black, white, black, white, black, white. Awesome. So guys, we have this field program working as well. Although we came across a few bugs in our program, but it was not that much challenging. In my case, actually I found programming in machine language easier than making all those chips, because for some of the previous chips that we built, I almost took more than 4 hours to build them, while for this two programs I built it inside just one stream. So that's good. Should we try to modify this program and draw a different kind of pattern? Let's see if we can tweak it a little bit and change the behavior of the program. We can do it inside this field. So what if I change only the if I jump one row? So let me show you what I mean. So instead of incrementing the address by 1, what if I increment it by 2? In that case I will have to modify it like this. I will have to first get 2 value inside the data register. I have inside d is equal to a, d contains 2. Now I can do at address. D is equal to, awesome. Let's see what it behaves like now. But A is an illegal. destination is n, so it is okay. What did we do? Oops, I think I messed up. Let me change it back to how it was. I hope this will fix it. Eight one nine one. Let's check if it fixed our program or not. Yeah, cool. Our program has been fixed. Now let's see how we can do that. How we can increment this variable by m by 2. First we are getting the address value. This m points to that value m. Now we are getting it inside a, and we are changing m is equal to d. What am I doing over here? First I'm getting value inside the data register. A is equal to m. M is equal to d. Getting the address. Now okay, I get it. Although I don't know why our previous code didn't work. M is equal to D. What does this address contain? Okay, it contains the address of that particular RAM. So it will start from the value of the screen. First we are getting the screen inside data register, and we are passing that value to this address variable. Right, now here we are getting the value which was either -1 or 0 inside this data register. After that we are passing we are first getting the address value inside A. Now this value, this contains the address. Now that this address is a pointer to another address, so therefore we are getting where this address points to inside A. Now that A we are changing to this value. Now after that, why can't I do this? Why can't I get at 2? This will load 2 inside A, right? After that, D is equal to A. And if I do M is equal to D. Let me try to run it again. Okay, this time it is not giving us any error. We'll change it to 8191 again. Okay, what is happening? 2 4 5 7 8. Wait, is it because I'm incrementing it by 2? Let me see. Why is it 2 4 5 7 8? Okay, there is no value of this kind. So error is for this m is equal to d. But what if this is not how we should change m? Do I have to write it like this? D is d plus m. Let's see if this makes any difference or not. No animation. Clear the program for 8191. Change to no animation. Now let's let it run. Okay, weird. Why is it giving us this kind of error? Okay, let me try to change this to 1 and see if it gives us any error this time. Eight one nine one. No animation. Awesome. Now I think I know why that was happening. It was because we can't increment it by 2. No, why can't we increment it by 2? We can increment it by 1, but we can't increment it by 2. Why? Because you can see clearly that they are consecutive. Each time we are increasing it by 1. Okay, wait, if we are increasing it by 2, then in the last unit it will not be 8191, it will surpass 8191, right? I think that might be causing the problem. Yeah, So we'll have to, for that to work, we'll have to change. Yeah, let me try something. Let me change it back to 2. And this time, first let me stop it and look at the program again. Program flow, let's clear the input. This time I'm not going to go 8191 but 8190. Let's see if this makes any difference or not. No animation. Awesome. Wait, not awesome. We're getting 24578. Now let's see how we can get 24578. 24578. And the base address is 16. Let me copy it. 16 minus 24578. 8194. Okay, so we are getting past 8190. It means so. Let me stop it and change the value again. This time let me pass a 8180. Wait, this time it does work, but I have to first I have to change it to no animation so that it doesn't stop to show us any animation. 8180. No animation. Oops. What's the last address? 8191. Two 4575 is the last address. We are getting past it. So why are we getting past it? We are jumping 2 steps. Okay, I get it now. We are jumping this by 2 steps, but we are not jumping I by 2 steps. We have to jump I by 2 steps as well. So let me copy this code and paste it over here. Now we can jump I by 2 steps as well. This might solve our problem. We can provide 8191 this time as well. Awesome. So this time, and let's see what kind of behavior it is giving. Oh, great. They're getting stripes now. So if we jump by, wait, why are we getting this type of pattern? We are jumping by row. Yeah. So we are jumping by row in the RAM. So that means this is the first. We are skipping this RAMs. And what if we want to get horizontal lines? What can we do to get the horizontal lines? Let's see, we need to jump the screen rows. We can use the this equation to jump the screen rows. But this is awesome. This looks awesome. We can again widen this gap if we can increase this 2 to 3, or let's say 4. If I increase it to 4, and run the program again. 192.191. Great, we widened the gap this time. Can get horizontal lines. So what if I want to write something on the screen, like a hello world? Okay, so displaying something is just a matter of finding a particular algorithm. So we can create a different algorithm for representing, fonts on the screen. You can select a pattern, a particular algorithm for all the different characters. For H, like H for something, a pattern for H, for E, hello, and all that. So I'm not gonna do that now. I've been streaming for almost 3 hours now, so I think I'm gonna take rest now. And this time we have completed the project section in just one stream, so I'm happy that we completed it inside just one stream. So next, let's see what is inside the next week's project. Next week we will be building the computer architecture. So we'll be building the memory, CPU, and computer. Okay, so finally we will have we will build up a complete computer. We will use all the chips that we built previously in the previous projects and assemble all of them to get a memory, entire memory space, a CPU, and a fully fledged computer. So it's great. So I will see you guys in the next stream. We will start with project 5, but before that I will have to review week 5's videos. So I will get back to this project after completing those videos. So I will see you guys in the next stream then. Have a nice day or night. Bye bye.